The following video is on L'Hopital's rule. The rule is named after Guillaume François Antoine de L'Hopital, who in true French fashion has a fabulous name. He lived from 1661 to 1704, and he was friends with Leibniz, who we've talked about earlier in this semester. Remember when we were trying to take the limit as x goes to 0 of 2 to the x minus 1 over x, we found that direct substitution gave us 0 over 0, which meant that we weren't allowed to do that. We couldn't simplify or factor. Multiplying by the conjugate didn't do anything good. And we tried to avoid the squeeze theorem because it's tricky. L'Hopital's rule is going to give us a way of evaluating this limit. It says given the limit as x goes to a of f of x over g of x, if direct substitution yields indeterminate forms of 0 over 0 and plus or minus infinity over plus or minus infinity, then the limit as x goes to a of f of x over g of x is the same thing as the limit as x goes to a of f prime of x over g prime of x. So in other words, we can take the derivative of the numerator and the derivative of the denominator, and the limit won't change. Let's try applying that to this problem now. Direct substitution gave us 0 over 0, so we're allowed to use L'Hopital's rule. So we take the derivative of the top, which we've seen is 2 to the x times ln of 2. We take the derivative of the bottom, which is 1. And now we try direct substitution. I get 2 to the 0 times ln of 2 over 1, which gives me ln of 2. And remember, this is what we saw that the limit should be going to. Warning, this L'Hopital's rule only works for indeterminate forms 0 over 0 or plus or minus infinity over plus or minus infinity. Let's look at another example. The limit as x goes to 0 of sine x over x. Direct substitution gives us 0 over 0, so we are allowed to use L'Hopital's rule. Taking the derivative of the top, we get cosine x, and taking the derivative of the bottom, we get 1, and we try direct substitution again. This time we get 1 over 1, which is 1. And remember, this was one of the limits that I told you to memorize. The limit as x goes to 0 of sine x over x goes to 1. Trying another one, the limit as x goes to infinity of 5x squared minus 10x plus 7 over e to the x. Direct substitution gives us infinity over infinity. Using L'Hopital's rule, we can take the derivative of the top and the derivative of the bottom to get the limit as x goes to infinity of 10x minus 10 over e to the x, and now do direct substitution again. Notice that we still get infinity over infinity. So we can use L'Hopital's rule again. We have the limit as x goes to infinity of 10 over e to the x. This time we get 10 over infinity, which we saw in a previous video goes to 0. So it's okay to use L'Hopital's rule multiple times as long as you keep getting indeterminate forms from the list above. We can also use L'Hopital's rule with things such as 0 times infinity. For example, let's look at the limit as x goes to 0 from above of x times ln of x. If we do direct substitution, I get 0 times negative infinity, which is an indeterminate form. I want to make this into a fraction in order to use L'Hopital's rule. So the trick that I'm going to do is I'm going to multiply the top and the bottom by 1 over x. Notice that the 1 over x and the x cancel in the numerator, and I'm left with the limit as x goes to 0 from above of natural log of x over 1 over x. Now I can do direct substitution and I get negative infinity over infinity, which is one of the valid indeterminate forms to use L'Hopital's rule with. Take the derivative of the top and the derivative of the bottom and simplify, and I'm left with the limit as x goes to 0 from above of 1 over x times negative x squared which is the same thing as the limit as x goes to 0 from above of negative x. Try direct substitution, and we get 0. For indeterminate forms with multiplication, this trick of dividing by 1 over x on the numerator and the denominator will always work. We can also use L'Hopital's rule with exponents. So these are any problems where direct substitution gives us 0 to the 0, 1 to the infinity, or infinity to the 0. For example, let's look at the limit as x goes to 0 of sine x to the x. Direct substitution gives us 0 to the 0. So what we're going to do is we're going to look at y equals sine x to the x. We're going to try to bring this exponent down. And the way that we do that is using the natural log. So I'm going to take the natural log of both sides of this equation in order to make the right-hand side look like x times natural log of sine x. Now we're going to look at the limit as x goes to 0 of the natural log of y instead of the limit as x goes to 0 from above of y. At the end, we'll try to get rid of this natural log. So direct substitution gave me 0 times negative infinity, which we saw earlier. We should use the trick of multiplying the top and the bottom by 1 over x. So I'm left with negative infinity over infinity when I do direct substitution. This allows me to use L'Hopital's rule. So I have the limit as x goes to 0 from above of the derivative of the top, which is 1 over sine x times cosine x, divided by the derivative of the bottom, which is negative 1 over x squared. So simplifying, I end up with cosine x over sine x times negative x squared. Direct substitution gives me infinity times 0, which again is an indeterminate form, so I'm going to use my trick. I'm going to keep the negative x squared on the top, and I'm going to push the sine x over cosine x into the bottom. So I'm left with the limit as x goes to 0 from above of negative x squared over tangent x. Direct substitution gives me 0 over 0, which is an indeterminate form, so I'm allowed to use L'Hopital's rule again. I have the limit as x goes to 0 from above of negative 2x over secant squared x, which direct substitution gives me 0 over 1. This is not an indeterminate form, this is equal to 0, not 1. So this limit equals 0. So notice that at the beginning we were looking at the natural log of y when we really wanted the limit as x goes to 0 of y. So instead we're going to say that the limit as x goes to 0 from above of y is going to be e to the whatever our limit was here, which is 0. So we end up with e to the 0, which is 1. Let's look at another example of this. Let's take the limit as x goes to infinity of 1 plus 1 over x to the x. Direct substitution gives me 1 to the infinity, which is one of the indeterminate forms. Once again, we're going to let y equal 1 plus 1 over x to the x. So the natural log of y is then the natural log of 1 plus 1 over x to the x, and we can bring the x out front. Now taking the limit as x goes to infinity of x times natural log of 1 plus 1 over x, direct substitution gives us infinity times 0, which is an indeterminate form. We can use our 1 over x trick on the numerator and denominator and get direct substitution yielding 0 over 0. This is an indeterminate form where we're allowed to use L'Hopital's rule. So by L'Hopital's rule, I take the derivative of the top divided by the derivative of the bottom. The derivative of the top is going to be 1 over 1 plus 1 over x times the derivative of 1 plus 1 over x, which is negative 1 over x squared, The derivative of the bottom is negative 1 over x squared. So notice that this simplifies to 1 over 1 plus 1 over x times negative 1 over x squared divided by negative 1 over x squared. So the negative 1 over x squareds cancel. Using direct substitution, I have 1 over 1 plus 0, which gives me 1. So, as x goes to infinity, the natural log of y goes to 1. But we didn't want the natural log of y, we wanted y. So to get rid of natural logs, we take e's. We raise both sides e to the. So we have y is now going to e to the 1, which is e.